Good day, everyone. Welcome to our presentation. Today, we are going to deliver a comprehensive critical review and performance evaluation of application layer messaging protocols within the Internet of Things ecosystem. This work has been developed at the Federal University of Pará in Belém, Brazil, by our research team consisting of Yasmim Sarmento, Emmanuel Cruz, Diego Oliveira, Bruno Lopes, and Taina Baia. Our core focus is to analyze, dissect, and supplement the notable scientific study published by researcher N. Naik, which evaluates the structural trade-offs and performance differences between four of the most widely adopted communication standards in the modern tech world: MQTT, COAP, AMQP, and HTTP. By bridging the gap between theoretical protocol design and practical network metrics, we aim to clarify how these technologies behave under different application constraints. Before we dive deep into the specific protocols, let us establish a solid foundational understanding of what the Internet of Things, or IoT, truly represents. At its core, the Internet of Things is a vast, decentralized network that connects millions of smart devices, embedding intelligence directly into our physical environment. This framework enables seamless data collection, processing, and real-time sharing among the devices themselves, and with centralized cloud infrastructures via the Internet. These systems are no longer composed of just traditional hosts like desktops or smartphones. Instead, they feature an entirely new class of hardware: microcontrollers, edge gateways, industrial actuators, and low-power sensors. These components work together to gather environmental metrics, trigger automated actions, and support intelligent decision-making systems across industries like smart cities, agriculture, healthcare, and home automation. Operating an Internet of Things network introduces strict engineering challenges that are fundamentally different from the traditional World Wide Web. First, we must deal with extreme resource constraints. Many IoT sensor nodes are tiny, battery-powered systems with severe limitations regarding processing capability, random access memory, and electrical power. Second, the nature of the data traffic is unique. We are usually transmitting small payloads, such as single temperature readings or status updates, meaning that a protocol with large unoptimized headers will waste precious wireless bandwidth on control data rather than actual utility. Third, these networks often communicate over highly unstable wireless links, characterized by frequent packet loss and deep latency fluctuations. Therefore, building an efficient system is a continuous exercise in design trade-offs. Network engineers must carefully balance protocol overhead, message delivery reliability, robust security mechanisms, and computational simplicity. To address these technical challenges, the industry has adopted several distinct application layer messaging protocols, each representing a very different architectural philosophy. First, we have MQTT, a highly optimized broker-based publish-subscribe model. It is designed to be extremely lightweight, making it ideal for frequent low-power telemetry using persistent TCP connections. Second, CoAP offers a binary RESTful approach designed by the IETF specifically for severely constrained networks. It runs over UDP to completely bypass connection establishment overhead and supports native resource observation. Third, AMQP is a robust enterprise messaging protocol. It handles complex message routing, transactional queues, and advanced security, prioritizing total system reliability over minimal resource consumption. Finally, HTTP remains the global web standard. It offers unmatched interoperability and absolute maturity, but it is notoriously heavy and inefficient for resource-constrained nodes due to its extensive text-based headers. Let us look closely at this structured comparison matrix, which synthesizes the key structural boundaries of the four protocols. When we examine the communication models, MQTT stands out with its asynchronous publish-subscribe model centered around a broker, while AMQP utilizes complex routable queues and exchanges. CoAP and HTTP, on the other hand, inherit the classic request-response paradigm, though CoAP adds an asynchronous observe expansion. Looking at the transport layer, MQTT, AMQP, and HTTP rely on the connection-oriented reliability of TCP, whereas CoAP utilizes the connectionless simplicity of UDP. This choice directly impacts header efficiency. MQTT boasts a tiny fixed header of only 2 bytes, and CoAP requires a compact 4 bytes. AMQP jumps to an 8-byte structure, while HTTP uses a completely variable verbose textual format. For security, MQTT and HTTP rely heavily on standard TLS or SSL. CoAP implements DTLS over UDP, and AMQP incorporates TLS along with SASL for advanced enterprise authentication. Because MQTT has emerged as a dominant standard for industrial monitoring and remote telemetry, it is essential to analyze its inner workings, specifically the role of the central broker and its built-in quality of service levels. The core strength of MQTT lies in the total spatial and temporal decoupling enabled by the publish-subscribe pattern. Publishers and subscribers never talk to each other directly. They interact entirely through the broker via logical topics. This decouples the endpoints completely. To manage reliability across unstable networks, MQTT introduces 3 explicit quality of service tiers. QoS Level 0, known as at most once, is a fast, best-effort delivery mechanism where messages are dispatched without any application-level acknowledgement. QoS Level 1, or at least once, guarantees that the message reaches its destination, though it may result in duplicate packets. Finally, QoS Level 2, or exactly once, utilizes a precise 4-way handshake to guarantee delivery while completely eliminating duplicates, providing maximum reliability at the expense of higher control overhead. Now let us transition into the empirical phase of our critical review by examining the experimental performance data collected within our testbed environment. This first chart presents a direct latency comparison between a persistent MQTT connection and a standard HTTP request-response cycle, measured in milliseconds. As indicated on the axis, lower values represent superior performance. The empirical results reveal a stark contrast. MQTT achieved an incredibly low latency, sitting close to 4.5 milliseconds, whereas the HTTP protocol exhibited a significantly higher delay, reaching approximately 21 milliseconds. This dramatic difference highlights the impact of protocol design. Because MQTT maintains an open, long-lived TCP connection with minimal binary overhead, it can transmit data packets almost instantaneously. HTTP, conversely, must deal with the repetitive processing of heavy, human-readable text headers for each independent exchange, adding substantial processing delays and network latency to the communication loop. Next, let us analyze the system performance from the perspective of message throughput, measured explicitly in total successfully processed messages per second. In this specific metric, higher values indicate a more efficient and powerful communication pipeline. The data illustrated in this chart mirrors the trends observed in our latency analysis, further validating the performance advantages of specialized IoT protocols. In our monitored scenario, the persistent MQTT architecture demonstrated exceptional scalability, managing to process a massive volume of approximately 1,500 messages every single second. In sharp contrast, the traditional HTTP framework maxed out at roughly 340 messages per second. This bottleneck occurs because the stateless nature of HTTP demands significant server-side overhead to parse incoming textual headers and open or close connection states repeatedly, whereas the streamlined binary architecture of the MQTT broker handles dense, high-frequency telemetry data streams with far greater efficiency. A vital element of our work involves performing a rigorous critical analysis of the original study published by Naik. On the positive side, the original article provides several major contributions to the field. It successfully consolidates and compares a broad range of protocols in a unified context, examining crucial multidimensional criteria such as quality of service mechanisms, security frameworks, and global interoperability across different vendor platforms. It explicitly avoids the naive conclusion that one protocol fits all scenarios. However, our review also identified substantial methodological limitations in the original text. The paper's primary flaw is the complete absence of a unified, hands-on experimental testbed comparing all four protocols under identical dynamic network behaviors. Furthermore, the original work fails to present critical experimental parameters, such as explicit payload sizes or repetition counts, and it completely ignores how varying network impairments like packet drops or jitter would alter protocol performance. In conclusion, our critical review reinforces the architectural principle that there is no single ideal protocol capable of satisfying every single Internet of Things scenario. The selection process must always be driven by specific system requirements. From a structural standpoint, MQTT and COAP are undeniably better suited for highly resource-constrained IoT endpoints and low-power telemetry pipelines. AMQP stands as the premier choice for complex enterprise integration environments where transactional queuing is mandatory, while HTTP remains vital due to its universal web interoperability and seamless cloud API integration. Empirically, our complementary evaluation proved that in high-frequency monitoring scenarios, MQTT delivers significantly lower latency and substantially higher message throughput than traditional HTTP. We hope this deep dive provides valuable insights for your future network designs. Thank you very much for your time and attention.